In this video we're going to try and get an intuitive understanding of the conversion to a floating point number. So we've seen before that we have a sign, we have an exponent, and we have the mantissa or the significand. And we've been using the single precision so far, so we've had 1 for the sign, we've had 8 for the exponent and 23 for this mantissa. Now the exponent here, we can think of the exponent as a range, and we can think about the mantissa as offering some precision. Also we could think about the range as existing between certain windows. So those windows are going to be each power of 2, and we're also going to have an offset which is going to be given by the mantissa. So let me show you what I mean by this. We know that the exponent is going to define the powers of 2. So for example, the exponent is going to run from 2 to the plus 127 and 2 to the minus 126. So let's say we split this line here from 2 to the 127, 2 to the minus 126 into the respective windows. So for example, we could have a window between 2 and 4 because those are powers of 2. We could have a window between 4 and 8. We could have a window between 8 and 16 to 32, and 32 to 64, and so on and so forth, all the way up to 2 to the power of 127. Now we can do the same in terms of the negative values, so this is going to give us our fractions. So we could have a window between minus a half, so we could have a window between a half and 0.25. We can have another window between 0.25 and half of that, which is 0.125, and we can have a window between half of the 0.125, which is 0.075, and 0.25. So this exponent allows us to shift up and down the number line. So in effect this gives us our range. If we had more values on the exponent, we would be able to represent a wider range of numbers. Now the mantissa here is going to provide us with an offset. So let's say for example we wanted to generate the number pi, and let's say we just wanted it to a couple of decimal places, say 3.14. So we know that pi is going to sit somewhere between 2 and 4. So we would have a value for our window which would start at a value of 2, but then we would have to add on the offset, and the offset would be given by this mantissa value. So this is one way of thinking about the floating point numbers. We can think about it as finding the number we're wanting to represent and just working out which window it's in. So the window will give us the exponent, and then we would have to work out how far along that window we have to come to get to the number. So how far along we have to come from 2 to get to this number 3.14 is the offset, and this offset is given by the mantissa. So let's continue this on the next page. So once we've defined the window we're using with the exponent, that window is going to be split into a certain number of portions. So those portions are going to be given by the mantissa. So we can think about those as little buckets which are going to contain number ranges. So in the single precision we have 23 bits for the mantissa. So we're going to have 2 to the 23, which is 8388608 different little buckets within each window. Now the more mantissa bits we have, the greater the precision we're going to get. But it also means that different windows are going to have different levels of precision. So let's look at two examples. Let's look at the range 2 to 4. So in the range 2 to 4, we're going to have a precision which is going to be 4 minus 2. so that's going to be the length of the window, and divided by the value here, 8388608, that's going to give us the precision of each bucket, and you can see here it's approximately 2.3 times 10 to the minus 7. Now if we were to go to the bucket further along, so if we went to one between the values 4096 and 2048, we subtract one from the other, so that's now going to be the new length of the window. So of course that new length of the window has got a larger area to fill than the 2 to the 4. So when we divide this out, we're going to have a precision of 0.0002, so that's only going to be down to 2 to the minus 4. So as always with floating point numbers, it's always best to see and understand by example. So let's say for example we're looking to represent pi to 2 decimal places, which is just going to be a value of plus 3.14. So we can split it into 3 parts here. We know that it's a positive, so we know that the sign is positive, therefore the sign bit is going to be a 0. The second part is looking at the exponent, but now we're looking at the exponent in terms of a window, and we're looking to find out what power of 2 does 3.14 lie between. So it's going to lie between the values 2 and 4. So that's going to be 2 to the power of 1 and 2 to the power of 2. So what we do is we take the lower value, so it's going to be 2 to the power of 1. So the exponent is actually going to be the value 2 to the power of 1. So what we've done here is we've worked out an approximation to 3.14, but all we've got to is the value of 2. We're still out by a certain amount, and the certain amount that we're out by here is going to be given by the mantissa. So just to finish this off, we're going to have a value of 1 for the exponent, but we know we have to add the bias, so the bias is plus 127. So we're going to have 127 plus 1 is going to be 128. So that's us got the second part. Now the third part is to find the mantissa. Now what the mantissa does is it provides us with our precision. So between 2 and 4 we know we're going to have 8388608 numbers, and we know we're going to have to go from the value 2 to the value 3.14. So all we have to do is just work out the percentage. So how far along from 2 to 4 are we going to get 3.14? Well, that's quite straightforward. If we take from 2 to 3.14, well, that's just going to give us a value of 1.14. So from here to here it's 1.14. So that's this value here, 3.14 minus 2. And that is a fraction of this distance here from 4 to 2. So that's a fraction of 2. So we just divide out by 4 minus 2 and we get our value of 0.57. So that's quite straightforward. We're only looking at how far along we come from 2 to 4 as a fraction, and we're going to then take that value, in this case is 0.57, and we're going to have to multiply it by the 8388608. So that's what we've done this line here. So we've multiplied this number here, which in effect is 2 to the 23, multiplied by 0.57, and we get 4781507. And that seems quite reasonable because 3.14 is just beyond halfway between the 2 and the 4. So in effect we've gone just beyond halfway along this length here of 8388608. So that's just a little bit more than half. So that's us finished. We've got our sign bit as 0, our exponent is 128, which is this number here whenever it's put into our binary, and our mantissa, which is the multiplication here which gives this number, is this number in binary. So what we can do is we can put all of these three together and we get this number here, and this is our 32-bit single precision floating point binary number. And I've also written it here in hex, So let's go ahead and we'll put it into one of our conversion tools just to check it out and make sure we have got the right answer. So I've opened up the conversion tool here. So if we put in our value 3.14, and you can see that we've got this binary value here, and the hex for it is 404.8F5C3, and that's the same as we've seen in the previous page. So it does work, and this is a much simpler and more intuitive way of looking at the conversion between a decimal and a single precision floating point binary number. So thank you for listening. I'll get you on the next video. Goodbye.